Photo of a bird in flight. Figure 2.1, the motion of an American kestrel through the air can be described by the bird's displacement, speed, velocity, and acceleration. When it flies in a straight line without any change in direction, its motion is said to be one-dimensional. Credit: Vince Maidens, Wikimedia Commons. Chapter outline. 2.1 Displacement. 2.2 Vectors, scalars, and coordinate systems. 2.3 Time, velocity and speed. 2.4 Acceleration. 2.5 Motion equations for constant acceleration in one dimension. 2.6 Problem-solving basics for one-dimensional kinematics. 2.7 Falling objects. 2.8 Graphical analysis of one-dimensional motion. Objects are in motion everywhere we look. Everything from a tennis game to a space probe flyby of the planet Neptune involves motion. When you are resting, your heart moves blood through your veins, and even in inanimate objects, there is continuous motion in the vibrations of atoms and molecules. Questions about motion are interesting in and of themselves. How long will it take for a space probe to get to Mars? Where will a football land if it is thrown at a certain angle? But an understanding of motion is also key to understanding other concepts in physics. An understanding of acceleration, for example, is crucial to the study of force. Our formal study of physics begins with kinematics, which is defined as the study of motion without considering its causes. The word kinematics comes from a Greek term meaning motion and is related to other English words such as cinema, movies, and kinesiology, the study of human motion. In one-dimensional kinematics and two-dimensional kinematics, we will study only the motion of a football, for example, without worrying about what forces cause or change its motion. Such considerations come in other chapters. In this chapter, we examine the simplest type of motion, namely, motion along a straight line or one-dimensional motion. In two-dimensional kinematics, we apply concepts developed here to study motion along curved paths, two- and three-dimensional motion, for example, that of a car rounding a curve. Define position, displacement, distance, and distance traveled. Explain the relationship between position and displacement. Distinguish between displacement and distance traveled. Calculate displacement and distance given initial position, final position, and the path between the two. 3 people cycling along a canal. The blurred buildings in the background convey a sense of motion of the cyclists. Figure 2.2, these cyclists in Vietnam can be described by their position relative to buildings and a canal. Their motion can be described by their change in position or displacement in the frame of reference. Credit: Susan Black, Photopedia. Position. In order to describe the motion of an object, you must first be able to describe its position, where it is at any particular time. More precisely, you need to specify its position relative to a convenient reference frame. Earth is often used as a reference frame, and we often describe the position of an object as it relates to stationary objects in that reference frame. For example, a rocket launch would be described in terms of the position of the rocket with respect to the Earth as a whole, while a professor's position could be described in terms of where she is in relation to the nearby whiteboard. See Figure 2.3. In other cases, we use reference frames that are not stationary but are in motion relative to the Earth. To describe the position of a person in an airplane, for example, we use the airplane, not the Earth, as the reference frame. See Figure 2.4. Displacement. If an object moves relative to a reference frame, for example, if a professor moves to the right relative to a whiteboard or a passenger moves toward the rear of an airplane, then the object's position changes. This change in position is known as displacement. The word displacement implies that an object has moved or has been displaced. Displacement. Displacement is the change in position of an object. Delta letter 1d465 equals letter 1d465f minus letter 1d4650. 2.1. Where delta letter 1d465 is displacement letter 1d465f, is the final position, and x0 is the initial position. In this text, the uppercase Greek letter delta. Delta always means change in whatever quantity follows it. Thus, delta letter 1d465 means change in position. Always solve for displacement by subtracting initial position x0. From final position, letter 1D465F. Note that the SI unit for displacement is the meter, m. See physical quantities and units, but sometimes kilometers, miles, feet, and other units of length are used. Keep in mind that when units other than the meter are used in a problem, you may need to convert them into meters to complete the calculation. The initial and final position of a professor as she moves to the right while writing on a whiteboard. Her initial position is 1.5 meters. Her final position is 3.5 meters. Her displacement is given by the equation delta x equals x sub f minus x sub 0 equals 2.0 meters. Figure 2.3, a professor paces left and right while lecturing. Her position relative to Earth is given by x. The plus 20 m. Displacement of the professor relative to Earth is represented by an arrow pointing to the right. View of an airplane with an inset of the passengers sitting inside. A passenger has just moved from his seat and is now standing in the back. His initial position was 6.0 meters. His final position is 2.0 meters. His displacement is given by the equation delta x equals x sub f minus x sub 0 equals 4.0 meters. Figure 2.4, a passenger moves from his seat to the back of the plane. His location relative to the airplane is given by x. The minus 40 m. Displacement of the passenger relative to the plane is represented by an arrow toward the rear of the plane. Notice that the arrow representing his displacement is twice as long as the arrow representing the displacement of the professor. He moves twice as far in figure 2.3. Note that displacement has a direction as well as a magnitude. The professor's displacement is 2m to the right, and the airline passenger's displacement is 4m toward the rear. In one-dimensional motion, direction can be specified with a plus or minus sign. When you begin a problem, you should select which direction is positive. Usually that will be to the right or up, but you are free to select positive as being any direction. The professor's initial position is letter 1D4650 equals 1, 5m. And her final position is letter 1D465F equals 3, 5m. Thus her displacement is delta letter 1D465 equals letter 1D465F minus letter 1D4650 equals 3, 5m minus 1, 5m equals plus 2, 0m. 2.2. In this coordinate system, motion to the right is positive, whereas motion to the left is negative. Similarly, the airplane passenger's initial position is letter 1D4650 equals 6, 0m. And his final position is letter 1D465F equals 2, 0m. So his displacement is delta letter 1D465 equals letter 1D465F minus letter 1D4650 equals 2, 0m minus 6, 0m equals minus 4, 0m. 2.3. His displacement is negative because his motion is toward the rear of the plane, or in the negative x. Direction in our coordinate system. Distance. Although displacement is described in terms of direction, distance is not. Distance is defined to be the magnitude or size of displacement between two positions. Note that the distance between two positions is not the same as the distance traveled between them. Distance traveled is the total length of the path traveled between two positions. Distance has no direction and thus no sign. For example, the distance the professor walks is 2m, the distance the airplane passenger walks is 4m. Misconception alert. Distance traveled versus magnitude of displacement. It is important to note that the distance traveled, however, can be greater than the magnitude of the displacement. By magnitude, we mean just the size of the displacement without regard to its direction. That is, just a number with a unit. For example, the professor could pace back and forth many times, perhaps walking a distance of 150 m during a lecture, yet still end up only 2 m to the right of her starting point. In this case, her displacement would be plus 20 m, the magnitude of her displacement would be 2m, but the distance she traveled would be 150 m. In kinematics, we nearly always deal with displacement and magnitude of displacement, and almost never with distance traveled. One way to think about this is to assume you mark the start of the motion and the end of the motion. The displacement is simply the difference in the position of the two marks, and is independent of the path taken in traveling between the two marks. The distance traveled, however, is the total length of the path taken between the two marks. Check your understanding. A cyclist rides 3 km west and then turns around and rides 2 km east. A. What is their displacement? B. What distance do they ride? C. What is the magnitude of their displacement? Solution. Two diagrams side by side. To the left is a horizontal line, or x-axis, with points for final position and initial position. Displacement 1, shown by an arrow pointing leftward, equals -3 kilometers. Displacement 2, shown by an arrow pointing rightward, equals 2 kilometers. To the right is a pair of x and y axes, showing that east is the positive x direction and west is the negative x direction. Figure 2.5. A. The rider's displacement is delta letter 1d465 equals letter 1d465f minus letter 1d465 equals minus 1 km. The displacement is negative because we take east to be positive and west to be negative. B. The distance traveled is 3 km plus 2 km equals 5 km. C. The magnitude of the displacement is 1 km. Learning objectives. By the end of this section, you will be able to define and distinguish between scalar and vector quantities. Assign a coordinate system for a scenario involving one-dimensional motion. A small jet airplane flying toward the left. Figure 2.6, the motion of this ellipse concept jet can be described in terms of the distance it has traveled, a scalar quantity, or its displacement in a specific direction, a vector quantity. In order to specify the direction of motion, its displacement must be described based on a coordinate system. In this case, it may be convenient to choose motion toward the left as positive motion. It is the forward direction for the plane, although in many cases the x coordinate runs from left to right, with motion to the right as positive and motion to the left as negative. Credit, Armchair Aviator Flicker. What is the difference between distance and displacement? Whereas displacement is defined by both direction and magnitude, distance is defined only by magnitude. Displacement is an example of a vector quantity. Distance is an example of a scalar quantity. A vector is any quantity with both magnitude and direction. Other examples of vectors include a velocity of 90 km/h east and a force of 500 newtons straight down. The direction of a vector in one-dimensional motion is given simply by a plus, or minus, sign. Vectors are represented graphically by arrows. An arrow used to represent a vector has a length proportional to the vector's magnitude, e.g., the larger the magnitude, the longer the length of the vector, and points in the same direction as the vector. Some physical quantities, like distance, either have no direction or none is specified. A scalar is any quantity that has a magnitude but no direction. For example, a 20 OC. Temperature, the 250 kilocalories, 250 calories of energy in a candy bar, a 90 km/h speed limit, a person's 1.8 m height, and a distance of 2 m are all scalars, quantities with no specified direction. Note, however, that a scalar can be negative, such as a -20 OC. Temperature, in this case, the minus sign indicates a point on a scale rather than a direction. Scalars are never represented by arrows. Coordinate systems for one-dimensional motion. In order to describe the direction of a vector quantity, you must designate a coordinate system within the reference frame. For one-dimensional motion, this is a simple coordinate system consisting of a one-dimensional coordinate line. In general, when describing horizontal motion, motion to the right is usually considered positive, and motion to the left is considered negative. With vertical motion, motion up is usually positive, and motion down is negative. In some cases, however, as with the jet in Figure 2.6, it can be more convenient to switch the positive and negative directions. For example, if you are analyzing the motion of falling objects, it can be useful to define downwards as the positive direction. If people in a race are running to the left, it is useful to define left as the positive direction. It does not matter as long as the system is clear and consistent. Once you assign a positive direction and start solving a problem, you cannot change it. An XY coordinate system. An arrow pointing toward the right shows the positive x direction. Negative x is toward the left. An arrow pointing up shows the positive y direction. Negative y points downward. Figure 2.7. It is usually convenient to consider motion upward or to the right as positive plus, and motion downward or to the left as negative minus. Check your understanding. A person's speed can stay the same as they round a corner and changes direction. Given this information, is speed a scalar or a vector quantity? Explain. Solution. Speed is a scalar quantity. It does not change at all with direction changes, therefore, it has magnitude only. If it were a vector quantity, it would change as direction changes, even if its magnitude remained constant. By the end of this section, you will be able to explain the relationships between instantaneous velocity, average velocity, instantaneous speed, average speed, displacement, and time. Calculate velocity and speed given initial position, initial time, final position, and final time. Derive a graph of velocity versus time, given a graph of position versus time. Interpret a graph of velocity versus time. Snails leaving slime trails as they race each other along a flat surface. Figure 2.8, the motion of these racing snails can be described by their speeds and their velocities. Credit, Ta by Tasflicker, Flicker. There is more to motion than distance and displacement. Questions such as, how long does a foot race take? And what was the runner's speed? Cannot be answered without an understanding of other concepts. In this section, we add definitions of time, velocity, and speed to expand our description of motion. Time. As discussed in physical quantities and units, the most fundamental physical quantities are defined by how they are measured. This is the case with time. Every measurement of time involves measuring a change in some physical quantity. It may be a number on a digital clock, a heartbeat, or the position of the sun in the sky. In physics, the definition of time is simple. Time is change, or the interval over which change occurs. It is impossible to know that time has passed unless something changes. The amount of time or change is calibrated by comparison with a standard. The SI unit for time is the second, abbreviated S. We might, for example, observe that a certain pendulum makes one full swing every 0.75 s. We could then use the pendulum to measure time by counting its swings or, of course, by connecting the pendulum to a clock mechanism that registers time on a dial. This allows us to not only measure the amount of time, but also to determine a sequence of events. How does time relate to motion? We are usually interested in elapsed time for a particular motion, such as how long it takes an airplane passenger to get from his seat to the back of the plane. To find elapsed time, we note the time at the beginning and end of the motion and subtract the two. For example, a lecture may start at 11:00 a.m. and end at 11:50 a.m., so that the elapsed time would be 50 min elapsed time delta letter 1D461. Is the difference between the ending time and beginning time. Delta letter 1D461 equals letter 1D461F minus letter 1D4610. 2.4. Where delta letter 1D461 is the change in time or elapsed time, letter 1D461F is the time at the end of the motion, and T0 is the time at the beginning of the motion. As usual, the delta symbol, delta, means the change in the quantity that follows it. Life is simpler if the beginning time T0 is taken to be 0, as when we use a stopwatch. If we were using a stopwatch, it would simply read 0 at the start of the lecture and 50 min at the end. If letter 1D4610 equals 0, then delta letter 1D461 equals letter 1D461F, identical to letter 1D461. In this text, for simplicity's sake, motion starts at time equal to 0. Letter 1D4610 equals 0. The symbol T is used for elapsed time unless otherwise specified. Delta letter 1D461 equals letter 1D461F, identical to letter 1D461. Velocity. Your notion of velocity is probably the same as its scientific definition. You know that if you have a large displacement in a small amount of time, you have a large velocity, and that velocity has units of distance divided by time, such as miles per hour or kilometers per hour. Average velocity. Average velocity is displacement, change in position, divided by the time of travel. Letter 1d463 equals delta letter 1d465 delta letter 1d461 equals letter 1d465f minus letter 1d4650 letter 1d461f minus letter 1d4610. 2.5. Where letter 1d463 is the average, indicated by the bar over the v. Velocity, delta letter 1d465, is the change in position or displacement, and letter 1d465f. And x0 are the final and beginning positions at times, letter 1d461f. And t0, respectively. If the starting time t0 is taken to be 0, then the average velocity is simply letter 1d463 equals delta letter 1d465 letter 1d461. 2.6. Notice that this definition indicates that velocity is a vector because displacement is a vector. It has both magnitude and direction. The SI unit for velocity is meters per second, or ms, but many other units, such as km/h, mph, also written as mph, and cm/s are in common use. Suppose, for example, an airplane passenger took 5 seconds to move minus 4m. The negative sign indicates that displacement is toward the back of the plane. His average velocity would be letter 1d463 equals delta letter 1d465 letter 1d461 equals minus 4m5s equals minus 0. 8 ms. 2.7. The minus sign indicates the average velocity is also toward the rear of the plane. The average velocity of an object does not tell us anything about what happens to it between the starting point and ending point, however. For example, we cannot tell from average velocity whether the airplane passenger stops momentarily or backs up before he goes to the back of the plane. To get more details, we must consider smaller segments of the trip over smaller time intervals. Airplane shown from the outside. Vector arrows show paths of each individual segment of the passenger's trip to the back of the plane. Figure 2.9, a more detailed record of an airplane passenger heading toward the back of the plane, showing smaller segments of his trip. The smaller the time intervals considered in a motion, the more detailed the information. When we carry this process to its logical conclusion, we are left with an infinitesimally small interval. Over such an interval, the average velocity becomes the instantaneous velocity or the velocity at a specific instant. A car's speedometer, for example, shows the magnitude, but not the direction of the instantaneous velocity of the car. Police give tickets based on instantaneous velocity, but when calculating how long it will take to get from one place to another on a road trip, you need to use average velocity. Instantaneous velocity v is the average velocity at a specific instant in time, or over an infinitesimally small time interval. Mathematically, finding instantaneous velocity v at a precise instant t can involve taking a limit, a calculus operation beyond the scope of this text. However, under many circumstances, we can find precise values for instantaneous velocity without calculus. Speed. In everyday language, most people use the terms speed and velocity interchangeably. In physics, however, they do not have the same meaning and they are distinct concepts. One major difference is that speed has no direction. Thus, speed is a scalar. Just as we need to distinguish between instantaneous velocity and average velocity, we also need to distinguish between instantaneous speed and average speed. Instantaneous speed is the magnitude of instantaneous velocity. For example, suppose the airplane passenger at one instant had an instantaneous velocity of minus 3.0 ms, the minus meaning toward the rear of the plane. At that same time, his instantaneous speed was 3 ms, or suppose that at one time during a shopping trip, your instantaneous velocity is 40 km/h due north. Your instantaneous speed at that instant would be 40 km/h, the same magnitude but without a direction. Average speed, however, is very different from average velocity. Average speed is the distance traveled divided by elapsed time. We have noted that distance traveled can be greater than the magnitude of displacement. So average speed can be greater than average velocity, which is displacement divided by time. For example, if you drive to a store and return home in half an hour, and your car's odometer shows the total distance traveled was 6 km, then your average speed was 12 km/h. Your average velocity, however, was 0 because your displacement for the round trip is 0. Displacement is change in position and thus is 0 for a round trip. Thus, average speed is not simply the magnitude of average velocity. A house and a store, with a set of arrows in between showing that the distance between them is 3.0 kilometers, and the total distance traveled, delta x total, equals 0 kilometers. Figure 2.1, during a 30-minute round trip to the store, the total distance traveled is 6 km. The average speed is 12 km/h. The displacement for the round trip is 0, since there was no net change in position. Thus, the average velocity is 0. Another way of visualizing the motion of an object is to use a graph. A plot of position or of velocity as a function of time can be very useful. For example, for this trip to the store, the position, velocity, and speed vs time graphs are displayed in Figure 2.11. Note that these graphs depict a very simplified model of the trip. We are assuming that speed is constant during the trip, which is unrealistic given that we'll probably stop at the store. But for simplicity's sake, we will model it with no stops or changes in speed. We are also assuming that the route between the store and the house is a perfectly straight line. 3-line graphs. First line graph is of position in kilometers versus time in hours. The line increases linearly from 0 kilometers to 3 kilometers in the first 0.25 hours. It then decreases linearly from 3 kilometers to 0 kilometers between 0.25 and 0.5 hours. Second line graph shows velocity in kilometers per hour versus time in hours. The line is flat at 12 kilometers per hour from time 0 to time 0.25. It is vertical at time 0.25, dropping from 12 kilometers per hour to negative 12 kilometers per hour. It is flat again at negative 12 kilometers per hour from 0.25 hours to 0.5 hours. Third line graph shows speed in kilometers per hour versus time in hours. The line is flat at 12 kilometers per hour from time equals 0 to time equals 0.5 hours. Figure 2.11, position versus time, velocity versus time, and speed versus time on a trip. Note that the velocity for the return trip is negative. Making connections, take-home investigation, getting a sense of speed. If you have spent much time driving, you probably have a good sense of speeds between about 10 and 70 miles per hour. But what are these in meters per second? What do we mean when we say that something is moving at 10 ms? To get a better sense of what these values really mean, do some observations and calculations on your own. Calculate typical car speeds in meters per second. Estimate jogging and walking speed by timing yourself. Convert the measurements into both ms and mph. Determine the speed of an ant, snail, or falling leaf. Check your understanding. A commuter train travels from Baltimore to Washington, D.C., and back in 1 hour and 45 minutes. The distance between the two stations is approximately 40 miles. What is A, the average velocity of the train, and B, the average speed of the train in ms? Solution. A, the average velocity of the train is 0, because letter 1d465f equals letter 1d4650. The train ends up at the same place it starts. B, the average speed of the train is calculated below. Note that the train travels 40 miles one way and 40 miles back for a total distance of 80 miles. Distance at time equals 80 miles 1 of 5 minutes. 2.8. 80 miles 5 minutes times 5,280 feet. 1 mile times 1 meter 328 feet times 1 minute 60 seconds equals 20 ms. 2.9. By the end of this section, you will be able to define and distinguish between instantaneous acceleration, average acceleration, and deceleration. Calculate acceleration given initial time, initial velocity, final time, and final velocity. An airplane flying very low to the ground, just above a beach full of onlookers, as it comes in for a landing. Figure 2.12, a plane decelerates or slows down as it comes in for landing in St. Martin. Its acceleration is opposite in direction to its velocity. Credit: Steve Conry, Flickr. In everyday conversation, to accelerate means to speed up. The accelerator in a car can in fact cause it to speed up. The greater the acceleration, the greater the change in velocity over a given time. The formal definition of acceleration is consistent with these notions, but more inclusive. Average acceleration. Average acceleration is the rate at which velocity changes. Letter 1d44e equals delta letter 1d463, delta letter 1d461 equals letter 1d463f, minus letter 1d463, 0, letter 1d461f, minus letter 1d461 0. 2.1. Where letter 1d44e is average acceleration, v, is velocity, and t is time, the bar over the a, means average acceleration. Because acceleration is velocity in ms divided by time in s, the SI units for acceleration are ms2. Meters per second squared or meters per second, which literally means by how many meters per second the velocity changes every second. Recall that velocity is a vector. It has both magnitude and direction. This means that a change in velocity can be a change in magnitude or speed, but it can also be a change in direction. For example, if a car turns a corner at constant speed, it is accelerating because its direction is changing. The quicker you turn, the greater the acceleration. So there is an acceleration when velocity changes either in magnitude, an increase or decrease in speed, or in direction, or both. Acceleration as a vector. Acceleration is a vector in the same direction as the change in velocity, delta letter 1d463. Since velocity is a vector, it can change either in magnitude or in direction. Acceleration is therefore a change in either speed or direction, or both. Keep in mind that although acceleration is in the direction of the change in velocity, it is not always in the direction of motion. When an object slows down, its acceleration is opposite to the direction of its motion. This is known as deceleration. A subway train arriving at a station. A velocity vector arrow points along the track away from the train. An acceleration vector arrow points along the track toward the train. Figure 2.13, a subway train in São Paulo, Brazil, decelerates as it comes into a station. It is accelerating in a direction opposite to its direction of motion. Credit: Yusu Kawasaki, Flickr. Misconception alert: deceleration versus negative acceleration. Deceleration always refers to acceleration in the direction opposite to the direction of the velocity. Deceleration always reduces speed. Negative acceleration, however, is acceleration in the negative direction in the chosen coordinate system. Negative acceleration may or may not be deceleration, and deceleration may or may not be considered negative acceleration. For example, consider figure 2.14. 4 separate diagrams of cars moving. Diagram A, a car moving toward the right. A velocity vector arrow points toward the right. An acceleration vector arrow also points toward the right. Diagram B, a car moving toward the right in the positive x direction. A velocity vector arrow points toward the right. An acceleration vector arrow points toward the left. Diagram C, a car moving toward the left. A velocity vector arrow points toward the left. An acceleration vector arrow points toward the right. Diagram D, a car moving toward the left. A velocity vector arrow points toward the left. An acceleration vector arrow also points toward the left. Figure 2.14, A, this car is speeding up as it moves toward the right. It therefore has positive acceleration in our coordinate system. B, this car is slowing down as it moves toward the right. Therefore, it has negative acceleration in our coordinate system because its acceleration is toward the left. The car is also decelerating. The direction of its acceleration is opposite to its direction of motion. C, this car is moving toward the left but slowing down over time. Therefore, its acceleration is positive in our coordinate system because it is toward the right. However, the car is decelerating because its acceleration is opposite to its motion. D, this car is speeding up as it moves toward the left. It has negative acceleration because it is accelerating toward the left. However, because its acceleration is in the same direction as its motion, it is speeding up, not decelerating. Example 2.1. Calculating acceleration. A racehorse leaves the gate. A racehorse coming out of the gate accelerates from rest to a velocity of 15 ms, due west in 1.8 s. What is its average acceleration? Two racehorses running toward the left. Figure 2.15, credit, John Sullivan, PD Photo.org. Strategy. First, we draw a sketch and assign a coordinate system to the problem. This is a simple problem, but it always helps to visualize it. Notice that we assign east as positive and west as negative. Thus, in this case, we have negative velocity. An acceleration vector arrow pointing west in the negative x direction, labeled with a equals question mark. A velocity vector arrow also pointing toward the left, with initial velocity labeled as 0 and final velocity labeled as negative 15.0 meters per second. Figure 2.16. We can solve this problem by identifying delta letter 1D463 and delta letter 1D461 from the given information, and then calculating the average acceleration directly from the equation letter 1D44E equals delta letter 1D463 delta letter 1D461 equals letter 1D463F minus letter 1D463 0 letter 1D461F minus letter 1D461 0. Solution. 1. Identify the knowns. Letter 1D4630 equals 0. Letter 1D463F equals minus 15, 0 ms. The negative sign indicates direction toward the west. Delta letter 1D461 equals 1, 80 s. 2. Find the change in velocity. Since the horse is going from 0 to minus 15, 0 ms. Its change in velocity equals its final velocity. Delta letter 1D463 equals letter 1D463F equals minus 15, 0 ms. 3. Plug in the known values, delta letter 1D463 and delta letter 1D461, and solve for the unknown letter 1D44E. Letter 1D44E equals delta letter 1D463, delta letter 1D461 equals minus 15. 0 ms 180 s equals minus 8, 33 ms 2. 2.11. Discussion. The negative sign for acceleration indicates that acceleration is toward the west. An acceleration of 8.33 ms 2. Due west means that the horse increases its velocity by 8.33 ms due west each second. That is, 8.33 meters per second, which we write as 8.33 ms2. This is truly an average acceleration, because the ride is not smooth. We shall see later that an acceleration of this magnitude would require the rider to hang on with a force nearly equal to his weight. Instantaneous acceleration. Instantaneous acceleration A, or the acceleration at a specific instant in time, is obtained by the same process as discussed for instantaneous velocity in time, velocity, and speed. That is, by considering an infinitesimally small interval of time. How do we find instantaneous acceleration using only algebra? The answer is that we choose an average acceleration that is representative of the motion. Figure 2.17 shows graphs of instantaneous acceleration versus time for two very different motions. In Figure 2.17, A, the acceleration varies slightly and the average over the entire interval is nearly the same as the instantaneous acceleration at any time. In this case, we should treat this motion as if it had a constant acceleration equal to the average, in this case about 1.8 ms2. In Figure 2.17b, the acceleration varies drastically over time. In such situations, it is best to consider smaller time intervals and choose an average acceleration for each. For example, we could consider motion over the time intervals from 0 to 1s and from 1 to 3s as separate motions with accelerations of plus 30 ms2 and 2 ms2, respectively. Line graphs of instantaneous acceleration in meters per second versus time in seconds. The line on graph A shows slight variation above and below an average acceleration of about 1.8 meters per second. The line on graph B shows great variation over time, with instantaneous acceleration constant at 3.0 meters per second for 1 second, then dropping to negative 2.0 meters per second for the next 2 seconds, and then rising again, and so forth. Figure 2.17 graphs of instantaneous acceleration versus time for two different one-dimensional motions. A. Here acceleration varies only slightly and is always in the same direction, since it is positive. The average over the interval is nearly the same as the acceleration at any given time. B. Here the acceleration varies greatly, perhaps representing a package on a post office conveyor belt that is accelerated forward and backward as it bumps along. It is necessary to consider small time intervals, such as from 0 to 1s, with constant or nearly constant acceleration in such a situation. The next several examples consider the motion of the subway train shown in Figure 2.18. In A, the shuttle moves to the right, and in B, it moves to the left. The examples are designed to further illustrate aspects of motion and to illustrate some of the reasoning that goes into solving problems. In Part A, a subway train moves from left to right from an initial position of x equals 4.7 kilometers to a final position of x equals 6.7 kilometers, with a displacement of 2.0 kilometers. In Part B, the train moves toward the left, from an initial position of 5.25 kilometers to a final position of 3.75 kilometers. Figure 2.18 one-dimensional motion of a subway train considered in Example 2.2, Example 2.3, Example 2.4, Example 2.5, Example 2.6, and Example 2.7. Here we have chosen the x-axis so that plus means to the right and minus means to the left for displacements, velocities, and accelerations. A. The subway train moves to the right from x0 to letter 1d465f. Its displacement delta, letter 1d465, is plus 20 km. B. The train moves to the left from letter 1d4650 to letter 1d465. Its displacement delta, letter 1d465, is minus 5 km. Note that the prime symbol is used simply to distinguish between displacement in the two different situations. The distances of travel and the size of the cars are on different scales to fit everything into the diagram. Example 2.2. Calculating displacement, a subway train. What are the magnitude and sign of displacements for the motions of the subway train shown in parts A and B of Figure 2.18? Strategy. A drawing with a coordinate system is already provided, so we don't need to make a sketch, but we should analyze it to make sure we understand what it is showing. Pay particular attention to the coordinate system. To find displacement, we use the equation delta letter 1d465 equals letter 1d465f minus letter 1d465 This is straightforward since the initial and final positions are given. Solution. 1. Identify the knowns. In the figure, we see that letter 1d465f equals 6, 70 km, and letter 1d4650 equals 4, 70 km. For part A, and letter 1d465 equals 3, 75 km, and letter 1d4650 equals 5, 25 km. For part B, 2. Solve for displacement in part A. Delta letter 1d465 equals letter 1d465f minus letter 1d4650 equals 6, 70 km minus 4, 70 km equals plus 2, 0, 0 km. 2.12. 3. Solve for displacement in part B. Delta letter 1d465 equals letter 1d465 minus letter 1d4650 equals 3, 75 km minus 5, 25 km equals minus 1, 50 km. 2.13. Discussion. The direction of the motion in A is to the right, and therefore its displacement has a positive sign, whereas motion in B is to the left and thus has a negative sign. Example 2.3. Comparing distance traveled with displacement, a subway train. What are the distances traveled for the motions shown in parts A and B of the subway train in Figure 2.18? Strategy. To answer this question, Think about the definitions of distance and distance traveled and how they are related to displacement. Distance between two positions is defined to be the magnitude of displacement, which was found in example 2.2. Distance traveled is the total length of the path traveled between the two positions. See displacement. In the case of the subway train shown in figure 2.18, the distance traveled is the same as the distance between the initial and final positions of the train. Solution. 1. The displacement for part A was plus 200 km. Therefore, the distance between the initial and final positions was 2 km, and the distance traveled was 2 km. 2. The displacement for part B was minus 5 km. Therefore, the distance between the initial and final positions was 1.5 km, and the distance traveled was 1.5 km. Discussion. Distance is a scalar. It has magnitude but no sign to indicate direction. Example 2.4. Calculating acceleration, a subway train speeding up. Suppose the train in figure 2.18, A accelerates from rest to 30 km/h in the first 20 s of its motion. What is its average acceleration during that time interval? Strategy. It is worth it at this point to make a simple sketch. A point represents the initial velocity of 0 kilometers per second. Below the point is a velocity vector arrow pointing to the right, representing the final velocity of 30.0 kilometers per hour. Below the velocity vector is an acceleration vector arrow labeled a equals question mark. Figure 2.19. This problem involves 3 steps. First, we must determine the change in velocity, then we must determine the change in time, and finally, we use these values to calculate the acceleration. Solution. 1. Identify the knowns. Letter 1D4630 equals 0. The train starts at rest. Letter 1D463F equals 30, 0 km/h. And delta letter 1D461 equals 20, 0 s. 2. Calculate delta letter 1D463. Since the train starts from rest, its change in velocity is delta letter 1D463 equals plus 30, 0 km/h, where the plus sign means velocity to the right. 3. Plug in known values and solve for the unknown letter 1D44e. Letter 1D44e equals delta letter 1D463, delta letter 1D461 equals plus 30, 0 km/h20, 0 s. 2.14. 4. Since the units are mixed, we have both hours and seconds for time, we need to convert everything into SI units of meters and seconds. See physical quantities and units for more guidance. Letter 1D44e equals plus 30 km/h20, 0 s, 103 m 1 km, 1 h 3600 s equals 0, 417 m s2. 2.15. Discussion. The plus sign means that acceleration is to the right. This is reasonable because the train starts from rest and ends up with a velocity to the right, also positive. So acceleration is in the same direction as the change in velocity, as is always the case. Example 2.5. Calculate acceleration, a subway train slowing down. Now suppose that at the end of its trip, the train in figure 2.18, A slows to a stop from a speed of 30 km/h in 8s. What is its average acceleration while stopping? Strategy. A velocity vector arrow pointing toward the right with initial velocity of 30.0 kilometers per hour and final velocity of 0. An acceleration vector arrow pointing toward the left, labeled a equals question mark. Figure 2.2. In this case, the train is decelerating, and its acceleration is negative because it is toward the left. As in the previous example, we must find the change in velocity and the change in time, and then solve for acceleration. Solution. 1. Identify the knowns. Letter 1D4630 equals 30, 0 km/h. Letter 1D463F equals 0 km/h. The train is stopped, so its velocity is 0, and delta letter 1D461 equals 8, 0, 0 s. 2. Solve for the change in velocity, delta letter 1D463. delta letter 1d463 equals letter 1d463f minus letter 1d463, 0 equals 0 minus 30. 0 km/h equals minus 30. 0 km/h. 2.16. 3. Plug in the knowns, delta letter 1d463 and delta letter 1d461, and solve for letter 1d44e. Letter 1d44e equals delta letter 1d463, delta letter 1d461 equals minus 30. 0 km/h8, 0, 0s. 2.17. 4. Convert the units to meters and seconds. Letter 1d44e equals delta letter 1d463, delta letter 1d461 equals minus 30. 0 km/h8, 0, 0s. 103 m1 km. 1h 3600 s equals minus 1, 0, 4 ms2. 2.18. Discussion. The minus sign indicates that acceleration is to the left. This sign is reasonable because the train initially has a positive velocity in this problem, and a negative acceleration would oppose the motion. Again, acceleration is in the same direction as the change in velocity, which is negative here. This acceleration can be called a deceleration because it has a direction opposite to the velocity. The graphs of position, velocity, and acceleration versus time for the trains in example 2.4 and example 2.5 are displayed in figure 2.21. We have taken the velocity to remain constant from 20 to 40s, after which the train decelerates. 3 graphs. The first is a line graph of position in meters versus time in seconds. The line begins at the origin and has a concave up shape from time equals 0 to time equals 20 seconds. It is straight with a positive slope from 20 seconds to 40 seconds. It is then convex up from 40 to 50 seconds. The second graph is a line graph of velocity in meters per second versus time in seconds. The line is straight with a positive slope beginning at the origin from 0 to 20 seconds. It is flat from 20 to 40 seconds. From 40 to 50 seconds, the line is straight with a negative slope back down to a velocity of 0. The third graph is a line graph of acceleration in meters per second versus time in seconds. The line is flat with a positive constant acceleration from 0 to 20 seconds. The line then drops to an acceleration of 0 from 20 to 40 seconds. The line drops again to a negative acceleration from 40 to 50 seconds. Figure 2.21, a position of the train over time. Notice that the train's position changes slowly at the beginning of the journey, then more and more quickly as it picks up speed. Its position then changes more slowly as it slows down at the end of the journey. In the middle of the journey, while the velocity remains constant, the position changes at a constant rate. B. Velocity of the train over time. The train's velocity increases as it accelerates at the beginning of the journey. It remains the same in the middle of the journey, where there is no acceleration. It decreases as the train decelerates at the end of the journey. C. The acceleration of the train over time. The train has positive acceleration as it speeds up at the beginning of the journey. It has no acceleration as it travels at constant velocity in the middle of the journey. Its acceleration is negative as it slows down at the end of the journey. Example 2.6. Calculating average velocity, the subway train. What is the average velocity of the train in part B of example 2.2, and shown again below, if it takes 5 min to make its trip? The train moves toward the left, from an initial position of 5.25 kilometers to a final position of 3.75 kilometers. Figure 2.22. Strategy. Average velocity is displacement divided by time. It will be negative here, since the train moves to the left and has a negative displacement. Solution. 1. Identify the knowns. Letter 1d465 equals 3, 75 km. Letter 1d4650 equals 5, 25 km. Delta letter 1d461 equals 5, 0, 0 min. 2. Determine displacement, delta letter 1d465. We found delta letter 1d465 to be minus 1, 5 km. In example 2.2. 3. Solve for average velocity. Letter 1d463 equals delta letter 1d465 delta letter 1d461 equals -1, 50 km 5, 0, 0. 2.19. 4 convert units. Letter 1d463 equals delta letter 1d465 delta letter 1d461 equals -1, 50 km 5, 0, 0 min. 60 min 1 h equals -18, 0 km/h. 2.2. Discussion. The negative velocity indicates motion to the left. Example 2.7. Calculating deceleration, the subway train. Finally, suppose the train in figure 2.22 slows to a stop from a velocity of 20 km/h in 10 s. What is its average acceleration? Strategy. Once again, let's draw a sketch. A velocity vector arrow pointing to the left with initial velocity of -20.0 km per hour and a final velocity of 0. An acceleration vector arrow pointing toward the right, labeled a equals question mark. Figure 2.23. As before, we must find the change in velocity and the change in time to calculate average acceleration. Solution. 1. Identify the knowns. Letter 1d4630 equals -20, 0 km/h. Letter 1d463f equals 0 km/h. Delta letter 1d461 equals 10, 0 s. 2. Calculate delta letter 1d463. The change in velocity here is actually positive, since delta letter 1d463 equals letter 1d463f minus letter 1d463, 0 equals 0 minus -20 km/h equals +20, 0 km/h. 2.21. 3. Solve for letter 1d44e. Letter 1d44e equals delta letter 1d463, delta letter 1d461 equals +20, 0 km/h 10, 0. 2.22. 4 convert units. Letter 1d44e equals +20, 0 km/h 10, 0, 103 m 1 km, 1 h 3600 s equals +0, 556 m/s2. 2.23. Discussion. The plus sign means that acceleration is to the right. This is reasonable because the train initially has a negative velocity, to the left, in this problem, and a positive acceleration opposes the motion, and so it is to the right. Again, acceleration is in the same direction as the change in velocity, which is positive here. As in example 2.5, this acceleration can be called a deceleration since it is in the direction opposite to the velocity. Sign and direction. Perhaps the most important thing to note about these examples is the signs of the answers. In our chosen coordinate system, plus means the quantity is to the right and minus means it is to the left. This is easy to imagine for displacement and velocity, but it is a little less obvious for acceleration. Most people interpret negative acceleration as the slowing of an object. This was not the case in example 2.7, where a positive acceleration slowed a negative velocity. The crucial distinction was that the acceleration was in the opposite direction from the velocity. In fact, a negative acceleration will increase a negative velocity. For example, the train moving to the left in figure 2.22 is sped up by an acceleration to the left. In that case, both v and a are negative. The plus and minus signs give the directions of the accelerations. If acceleration has the same sign as the velocity, the object is speeding up. If acceleration has the opposite sign as the velocity, the object is slowing down. Check your understanding. An airplane lands on a runway traveling east. Describe its acceleration. PH at explorations. Moving man simulation. Learn about position, velocity, and acceleration graphs. Move the little man back and forth with the mouse and plot his motion. Set the position, velocity, or acceleration, and let the simulation move the man for you. Click to view content. Learning objectives. By the end of this section, you will be able to calculate displacement of an object that is not accelerating, given initial position and velocity. Calculate final velocity of an accelerating object, given initial velocity, acceleration, and time. Calculate displacement and final position of an accelerating object, given initial position, initial velocity, time, and acceleration. 4 men racing up a river in their kayaks. Figure 2.24 kinematic equations can help us describe and predict the motion of moving objects, such as these kayaks racing in Newbury, England. Credit: Bari Skeets Flickr. We might know that the greater the acceleration of, say, a car moving away from a stop sign, the greater the displacement in a given time. But we have not developed a specific equation that relates acceleration and displacement. In this section, we develop some convenient equations for kinematic relationships, starting from the definitions of displacement, velocity, and acceleration already covered. Notation: TXV. First, let us make some simplifications in notation. Taking the initial time to be 0, as if time is measured with a stopwatch, is a great simplification. Since elapsed time is delta letter 1d461 equals letter 1d461f minus letter 1d4610. Taking letter 1d4610 equals 0 means that the final time on the stopwatch, when initial time is taken to be 0, we use the subscript 0 to denote initial values of position and velocity. That is, x0 is the initial position and v0 is the initial velocity. We put no subscripts on the final values. That is, t is the final time, x is the final position, and v is the final velocity. This gives a simpler expression for elapsed time. Now, delta letter 1d461 equals letter 1d461. It also simplifies the expression for displacement, which is now delta letter 1d465 equals letter 1d465 minus letter 1d465. Also, it simplifies the expression for change in velocity, which is now delta letter 1d463 equals letter 1d463 minus letter 1d463. To summarize, using the simplified notation, with the initial time taken to be 0, delta letter 1d461, delta letter 1d465, delta letter 1d463 equals letter 1d461 letter 1d465 minus letter 1d465 0 letter 1d463 minus letter 1d463. 2.24, where the subscript 0 denotes an initial value and the absence of a subscript denotes a final value in whatever motion is under consideration. We now make the important assumption that acceleration is constant. This assumption allows us to avoid using calculus to find instantaneous acceleration. Since acceleration is constant, the average and instantaneous accelerations are equal. That is, letter 1d44 equals letter 1d44 equals constant. 2.25. So we use the symbol A for acceleration at all times. Assuming acceleration to be constant does not seriously limit the situations we can study nor degrade the accuracy of our treatment. For one thing, acceleration is constant in a great number of situations. Furthermore, in many other situations, we can accurately describe motion by assuming a constant acceleration equal to the average acceleration for that motion. Finally, in motions where acceleration changes drastically, such as a car accelerating to top speed and then braking to a stop, the motion can be considered in separate parts, each of which has its own constant acceleration. Solving for displacement, delta letter 1d465, and final position, x, from average velocity when acceleration a is constant. To get our first two new equations, we start with the definition of average velocity. Letter 1d463 equals delta letter 1d465 delta letter 1d461. 2.26. Substituting the simplified notation for delta letter 1d465 and delta letter 1d461 yields letter 1d463 equals letter 1d465 minus letter 1d465 0 letter 1d461. 2.27. Solving for x yields letter 1d465 equals letter 1d465 0 plus letter 1d463 letter 1d461. 2.28. where the average velocity is letter 1D463 equals letter 1D4630 plus letter 1D463, 2C, ONST, a NT letter 1D440. 2.29. The equation letter 1D463 equals letter 1D4630 plus letter 1D4632 reflects the fact that, when acceleration is constant, v is just the simple average of the initial and final velocities. For example, if you steadily increase your velocity, that is, with constant acceleration, from 30 to 60 km/h, then your average velocity during this steady increase is 45 km/h. Using the equation letter 1D463 equals letter 1D4630 plus letter 1D4632. To check this, we see that letter 1D463 equals letter 1D4630 plus letter 1D463, 2 equals 30 km/h plus 60 km/h2 equals 45 km/h. 2.3. Which seems logical. Example 2.8. Calculating displacement, how far does the jogger run? A jogger runs down a straight stretch of road with an average velocity of 4 ms for 2 min. What is his final position, taking his initial position to be 0? Strategy. Draw a sketch. Velocity vector arrow, labeled v, equals 4.00 meters per second over an x-axis, displaying initial and final positions. Final position is labeled x equals question mark. Figure 2.25. The final position, x, is given by the equation letter 1D465 equals letter 1D4650 plus letter 1D463, letter 1D461. 2.31. To find x, we identify the values of x0, letter 1D463, and t from the statement of the problem and substitute them into the equation. Solution. 1. Identify the knowns. Letter 1D463 equals 4, 0, 0 ms. Delta letter 1D461 equals 2, 0, 0 min. And letter 1D4650 equals 0 m. 2. Enter the known values into the equation. Letter 1D465 equals letter 1D4650 plus letter 1D463, letter 1D461 equals 0 plus 4, 0, 0 m/s. 120 s equals 480 m. 2.32. Discussion. Velocity and final displacement are both positive, which means they are in the same direction. The equation letter 1D465 equals letter 1D4650 plus letter 1D463, letter 1D461 gives insight into the relationship between displacement, average velocity, and time. It shows, for example, that displacement is a linear function of average velocity. By linear function, we mean that displacement depends on letter 1D463 rather than on letter 1D463 raised to some other power, such as letter 1D4632. When graphed, linear functions look like straight lines with a constant slope. On a car trip, for example, we will get twice as far in a given time if we average 90 km/h than if we average 45 km/h. Line graph showing displacement in meters versus average velocity in meters per second. The line is straight with a positive slope. Displacement x increases linearly with increase in average velocity v. Figure 2.26, there is a linear relationship between displacement and average velocity for a given time t. An object moving twice as fast as another object will move twice as far as the other object. Solving for final velocity, we can derive another useful equation by manipulating the definition of acceleration. Letter 1D440 equals delta letter 1D463, delta letter 1D461. 2.33. Substituting the simplified notation for delta letter 1D463 and delta letter 1D461 gives us letter 1D440 equals letter 1D463 minus letter 1D463, 0 letter 1D461. CONST, a NT letter 1D440. 2.34. Solving for v yields Letter 1d463 equals letter 1d4630 plus letter 1d44 letter 1d461. CONST at NT letter 1d44. 2.35. Example 2.9. Calculating final velocity. An airplane slowing down after landing. An airplane lands with an initial velocity of 70 ms and then decelerates at 1.5 ms2. For 40s, what is its final velocity? Strategy. Draw a sketch. We draw the acceleration vector in the direction opposite the velocity vector because the plane is decelerating. Velocity vector arrow pointing toward the right in the positive x direction. Initial velocity equals 70 meters per second. Final velocity equals question mark. An acceleration vector arrow pointing toward the left labeled at equals negative 1.50 meters per second squared. Figure 2.27. Solution. 1. Identify the knowns. Letter 1d4630 equals 70, 0 ms. Letter 1d44 equals minus 1, 50 ms2. Letter 1d461 equals 40, 0. 2. Identify the unknown. In this case, it is final velocity, letter 1d463f. 3. Determine which equation to use. We can calculate the final velocity using the equation letter 1d463 equals letter 1d4630 plus letter 1d44 letter 1d461. 4. Plug in the known values and solve. Letter 1d463 equals letter 1d4630 plus letter 1d44 letter 1d461 equals 70, 0 m/s plus, minus 1, 50 m/s2, 40, 0 s equals 10, 0 ms. 2.36. Discussion. The final velocity is much less than the initial velocity, as desired when slowing down, but still positive. With jet engines, reverse thrust could be maintained long enough to stop the plane and start moving it backward. That would be indicated by a negative final velocity, which is not the case here. An airplane moving toward the right at 2 points in time. At time equals 0, the velocity vector arrow points toward the right and is labeled 70 meters per second. The acceleration vector arrow points toward the left and is labeled negative 1.5 meters per second squared. At time equals 40 seconds, the velocity arrow is shorter, points toward the right, and is labeled 10 meters per second. The acceleration vector arrow is still pointing toward the left and is labeled at equals negative 1.5 meters per second squared. Figure 2.28, the airplane lands with an initial velocity of 70 ms and slows to a final velocity of 10 ms before heading for the terminal. Note that the acceleration is negative because its direction is opposite to its velocity, which is positive. In addition to being useful in problem solving, the equation letter 1d463 equals letter 1d4630 plus letter 1d44 letter 1d461 gives us insight into the relationships among velocity, acceleration, and time. From it we can see, for example, that final velocity depends on how large the acceleration is and how long it lasts. If the acceleration is 0, then the final velocity equals the initial velocity. Letter 1d463 equals letter 1d4630. As expected, i.e., velocity is constant. If a is negative, then the final velocity is less than the initial velocity. All of these observations fit our intuition, and it is always useful to examine basic equations in light of our intuition and experiences to check that they do indeed describe nature accurately. Making connections, real-world connection. Space shuttle blasting off at night. Figure 2.29, the Space Shuttle Endeavour blasts off from the Kennedy Space Center in February 2010. Credit: Matthew Simantov, Flickr. An intercontinental ballistic missile, ICBM, has a larger average acceleration than the Space Shuttle and achieves a greater velocity in the first minute or two of flight. Actual ICBM burn times are classified. Short burn time missiles are more difficult for an enemy to destroy. But the Space Shuttle obtains a greater final velocity, so that it can orbit the Earth rather than come directly back down as an ICBM does. The Space Shuttle does this by accelerating for a longer time. Solving for final position when velocity is not constant, letter 1d4 not equal to 0. We can combine the equations above to find a third equation that allows us to calculate the final position of an object experiencing constant acceleration. We start with letter 1d463 equals letter 1d4630 plus letter 1d44 letter 1d461. 2.37. Adding v0 to each side of this equation and dividing by 2 gives letter 1d4630 plus letter 1d463, 2 equals letter 1d4630 plus 12 letter 1d44 letter 1d461. 2.38. Since letter 1d4630 plus letter 1d463, 2 equals letter 1d463. For constant acceleration, then, letter 1d463 equals letter 1d4630 plus 12 letter 1d44 letter 1d461. 2.39. Now we substitute this expression for letter 1d463 into the equation for displacement. Letter 1d465 equals letter 1d4650 plus letter 1d463 letter 1d461. Yielding letter 1d465 equals letter 1d4650 plus letter 1d4630 letter 1d461 plus 12 letter 1d44 letter 1d461 2 const at nt letter 1d44. 2.4. Example 2.1. Calculating displacement of an accelerating object. Dragsters. Dragsters can achieve average accelerations of 26 ms2. Suppose such a dragster accelerates from rest at this rate for 5.56 s. How far does it travel in this time? Dragster accelerating down a racetrack. Figure 2.3. U.S. Army top fuel pilot Tony, the Sarge Schumacher begins a race with a controlled burnout. Credit, LT, call William Thurmond. Photo courtesy of U.S. Army. Strategy. Draw a sketch. Acceleration vector arrow pointing toward the right in the positive x direction, labeled a equals 26.0 meters per second squared. X position graph with initial position at the left end of the graph. The right end of the graph is labeled x equals question mark. Figure 2.31. We are asked to find displacement, which is x. If we take x0 to be 0, think about it like the starting line of a race. It can be anywhere, but we call it and measure all other positions relative to it. We can use the equation letter 1d465 equals letter 1d4650 plus letter 1d4630 letter 1d461 plus 12 letter 1d44 letter 1d461 2. Once we identify v0, a, and t from the statement of the problem. Solution. 1. Identify the knowns. Starting from rest means that letter 1d4630 equals 0. A is given as 26 ms2, and t is given as 5.56 s. 2. Plug the known values into the equation to solve for the unknown x. Letter 1d465 equals letter 1d4650 plus letter 1d4630 letter 1d461 plus 12 letter 1d44 letter 1d461 2. 2.41. Since the initial position and velocity are both 0, this simplifies to letter 1d465 equals 12 letter 1d44 letter 1d461 2. 2.42. Substituting the identified values of a and t gives letter 1d465 equals 12, 26, 0 m/s2, 5, 56 s2. 2.43. Yielding m. 2.44. Discussion. If we convert 402 m to miles, we find that the distance covered is very close to 1/4 of a mile, the standard distance for drag racing. So the answer is reasonable. This is an impressive displacement in only 5.56 s, but top-notch dragsters can do a 1/4 mile in even less time than this. What else can we learn by examining the equation letter 1d465 equals letter 1d4650 plus letter 1d463 letter 1d461, plus 12, letter 1d44, letter 1d461, 2. We see that displacement depends on the square of the elapsed time when acceleration is not 0. In example 2.1, the dragster covers only 1/4 of the total distance in the first half of the elapsed time. If acceleration is 0, then the initial velocity equals average velocity, letter 1d4630 equals letter 1d463, and letter 1d465 equals letter 1d4650 plus letter 1d4630, letter 1d461, plus 12, letter 1d44, letter 1d461, 2. Becomes letter 1d465 equals letter 1d4650, plus letter 1d4630, letter 1d461. Solving for final velocity when velocity is not constant, letter 1d440 not equal to 0. A fourth useful equation can be obtained from another algebraic manipulation of previous equations. If we solve letter 1d463 equals letter 1d4630 plus letter 1d44, letter 1d461. For t, we get letter 1d461 equals letter 1d463 minus letter 1d463, 0, letter 1d440. 2.45. Substituting this and letter 1d463 equals letter 1d4630 plus letter 1d4632. Into letter 1d465 equals letter 1d4650 plus letter 1d463, letter 1d461. We get letter 1d463, 2 equals letter 1d463, 20, plus 2, letter 1d440, letter 1d465 minus letter 1d465, CONST, a NT, letter 1d440. 2.46. Example 2.11. Calculating final velocity, dragsters. Calculate the final velocity of the dragster in example 2.1 without using information about time. Strategy. Draw a sketch. Acceleration vector arrow pointing toward the right, labeled 26.0 meters per second squared. Initial velocity equals 0. Final velocity equals question mark. Figure 2.32. The equation letter 1d463, 2 equals letter 1d463, 20 plus 2, letter 1d440. Letter 1d465 minus letter 1d465, is ideally suited to this task because it relates velocities, acceleration, and displacement, and no time information is required. Solution. 1. Identify the known values. We know that letter 1d4630 equals 0. Since the dragster starts from rest. Then we note that letter 1d465 minus letter 1d4650 equals 402 m. This was the answer in example 2.1. Finally, the average acceleration was given to be letter 1d440 equals 26, 0 ms2. 2. Plug the knowns into the equation letter 1d463, 2 equals letter 1d463, 20 plus 2, letter 1d440. Letter 1d465 minus letter 1d465, and solve for v. Letter 1d4632 equals 0 plus 2, 26, 0 m/s2, 402 m. 2.47. Thus, letter 1d463, 2 equals 2, 0 9 times 104 m2/s2. 2.48. To get v, we take the square root. Letter 1d463 equals 2, 0 9 times 104 m2/s2 square equals 145 ms. 2.49. Discussion. 145 ms is about 522 km/h, or about 324 mph, but even this breakneck speed is short of the record for the quarter mile. Also, note that a square root has two values. We took the positive value to indicate a velocity in the same direction as the acceleration. An examination of the equation letter 1d463, 2 equals letter 1d463, 20 plus 2, letter 1d440. Letter 1d465 minus letter 1d465, can produce further insights into the general relationships among physical quantities. The final velocity depends on how large the acceleration is and the distance over which it acts. For a fixed deceleration, a car that is going twice as fast doesn't simply stop in twice the distance. It takes much further to stop. This is why we have reduced speed zones near schools. Putting equations together. In the following examples, we further explore one-dimensional motion, but in situations requiring slightly more algebraic manipulation. The examples also give insight into problem-solving techniques. The box below provides easy reference to the equations needed. Summary of kinematic equations, constant A. Letter 1d465 equals letter 1d4650 plus letter 1d463, letter 1d461. 2.5. Letter 1d463 equals letter 1d4630 plus letter 1d4632. 2.51. Letter 1d463 equals letter 1d4630 plus letter 1d44 letter 1d461. 2.52. Letter 1d465 equals letter 1d4650 plus letter 1d4630 letter 1d461 plus 12 letter 1d44 letter 1d461 2. 2.53. Letter 1d463 2 equals letter 1d463 20 plus 2 letter 1d440. Letter 1d465 minus letter 1d4650. 2.54. Example 2.12. Calculating displacement. How far does a car go when coming to a halt? On dry concrete, a car can decelerate at a rate of 7 ms2. Whereas on wet concrete, it can decelerate at only 5 ms2. Find the distances necessary to stop a car moving at 30 ms, about 110 km/h, A, on dry concrete and B, on wet concrete. C, repeat both calculations, finding the displacement from the point where the driver sees a traffic light turn red, taking into account his reaction time of 0.5 s to get his foot on the brake. Strategy. Draw a sketch. Initial velocity equals 30 meters per second. Final velocity equals 0. Acceleration dry equals negative 7.00 meters per second squared. Acceleration wet equals negative 5.00 meters per second squared. Figure 2.33. In order to determine which equations are best to use, we need to list all of the known values and identify exactly what we need to solve for. We shall do this explicitly in the next several examples, using tables to set them off. Solution for A. 1. Identify the knowns and what we want to solve for. We know that letter 1d4630 equals 30, 0 ms. Letter 1d463 equals 0. Letter 1d440 equals minus 7, 0 m/s2. A is negative because it is in a direction opposite to velocity. We take x0. To b0, we are looking for displacement delta letter 1d465, or letter 1d465 minus letter 1d4650. 2. Identify the equation that will help us solve the problem. The best equation to use is letter 1d463 2 equals letter 1d463 20 plus 2 letter 1d440. Letter 1d465 minus letter 1d465 2.55. This equation is best because it includes only one unknown, x. We know the values of all the other variables in this equation. There are other equations that would allow us to solve for x, but they require us to know the stopping time, t, which we do not know. We could use them, but it would entail additional calculations. 3. Rearrange the equation to solve for x. Letter 1d465 minus letter 1d465, 0, equals letter 1d463, 2 minus letter 1d463, 202 letter 1d440. 2.56. 4. Enter known values. Letter 1d465 minus 0 equals 0 2 minus 30, 0 m/s22 minus 7, 0 ms2. 2.57. Thus, letter 1d465 equals 64, 3 m on dry concrete. 2.58. Solution for B. This part can be solved in exactly the same manner as part A. The only difference is that the deceleration is 5 ms2. The result is letter 1d465 wet equals 90, 0 m on wet concrete. 2.59. Solution for C. Once the driver reacts, the stopping distance is the same as it is in parts A and B for dry and wet concrete. So to answer this question, we need to calculate how far the car travels during the reaction time, and then add that to the stopping time. It is reasonable to assume that the velocity remains constant during the driver's reaction time. 1. Identify the knowns and what we want to solve for. We know that letter 1d463 equals 30, 0 ms. Letter 1d461 reaction equals 0, 5 hundredths. Letter 1d44 reaction equals 0. We take letter 1d465, 0 minus reaction. To be 0, we are looking for letter 1d465 reaction. 2. Identify the best equation to use. Letter 1d465 equals letter 1d465 0 plus letter 1d463, letter 1d461. Works well because the only unknown value is x, which is what we want to solve for. 3. Plug in the knowns to solve the equation. Letter 1d465 equals 0 plus 30, 0 m slash s, 0. 500 s equals 15, 0 m. 2.6. This means the car travels 15 m while the driver reacts, making the total displacements in the two cases of dry and wet concrete 15 m greater than if he reacted instantly. 4. Add the displacement during the reaction time to the displacement when braking. Letter 1d465 braking plus letter 1d465 reaction equals letter 1d465 total. 2.61. 64.3 m plus 15 m equals 79.3 m when dry. 90 m plus 15 m equals 105 m when wet. Diagram showing the various braking distances necessary for stopping a car. With no reaction time considered, braking distance is 64.3 meters on a dry surface and 90 meters on a wet surface. With reaction time of 0.500 seconds, braking distance is 79.3 meters on a dry surface and 105 meters on a wet surface. Figure 2.34. The distance necessary to stop a car varies greatly, depending on road conditions and driver reaction time. Shown here are the braking distances for dry and wet pavement, as calculated in this example. For a car initially traveling at 30 ms, also shown are the total distances traveled from the point where the driver first sees a light turn red, assuming a 0.5 s reaction time. Discussion. The displacements found in this example seem reasonable for stopping a fast-moving car. It should take longer to stop a car on wet rather than dry pavement. It is interesting that reaction time adds significantly to the displacements, but more important is the general approach to solving problems. We identify the knowns and the quantities to be determined and then find an appropriate equation. There is often more than one way to solve a problem. The various parts of this example can in fact be solved by other methods, but the solutions presented above are the shortest. Example 2.13. Calculating time, a car merges into traffic. Suppose a car merges into freeway traffic on a 200 m long ramp. If its initial velocity is 10 ms and it accelerates at 2 ms2, how long does it take to travel the 200 m up the ramp? Such information might be useful to a traffic engineer. Strategy. Draw a sketch. A line segment with ends labeled x sub 0 equals 0 and x equals 200. Above the line segment, the equation t equals question mark indicates that time is unknown. 3 vectors, all pointing in the direction of x equals 200, represent the other knowns and unknowns. They are labeled v sub 0 equals 10.0 meters per second, v equals question mark, and a equals 2.00 meters per second squared. Figure 2.35. We are asked to solve for the time t. As before, we identify the known quantities in order to choose a convenient physical relationship. That is, an equation with one unknown, t. Solution. 1. Identify the knowns and what we want to solve for. We know that letter 1d4630 equals 10 ms. Letter 1d440 equals 2, 0, 0 ms2. And letter 1d465 equals 200 m. 2. We need to solve for t. Choose the best equation. Letter 1d465 equals letter 1d4650 plus letter 1d4630, letter 1d461, plus 12 letter 1d44, letter 1d461, 2. Works best because the only unknown in the equation is the variable t, for which we need to solve. 3. We will need to rearrange the equation to solve for t. In this case, it will be easier to plug in the knowns first. 200m equals 0m plus 10, 0m slash s letter 1d461 plus 12, 2, 0, 0m slash s2 letter 1d461, 2. 2.62. 4. Simplify the equation. The units of meters, m, cancel because they are in each term. We can get the units of seconds, s, to cancel by taking letter 1d461 equals letter 1d461s, where t is the magnitude of time and s is the unit. Doing so leaves 200 equals 10 letter 1d461 plus letter 1d461, 2. 2.63. 5. Use the quadratic formula to solve for t. A. Rearrange the equation to get 0 on one side of the equation. Letter 1d461, 2, plus 10 letter 1d461 minus 200 equals 0. 2.64. This is a quadratic equation of the form letter 1d44, letter 1d461, 2, plus letter 1d44f, letter 1d461, plus letter 1d450 equals 0. 2.65. Where the constants are letter 1d440 equals 1, 0, 0, letter 1d44f equals 10, 0, and letter 1d450 equals minus 200. B. Its solutions are given by the quadratic formula. Letter 1d461 equals minus letter 1d44f, plus or minus letter 1d44f, 2 minus 4 letter 1d44, letter 1d450, square 2 letter 1d440. 2.66. This yields two solutions for t, which are letter 1d461 equals 10, 0 and minus 20, 0. 2.67. In this case, then, the time is letter 1d461 equals letter 1d461 in seconds, or letter 1d461 equals 10, 0 and minus 20, zeros. 2.68. A negative value for time is unreasonable, since it would mean that the event happened 20s before the motion began. We can discard that solution. Thus, letter 1d461 equals 10, zeros. 2.69. Discussion. Whenever an equation contains an unknown squared, there will be two solutions. In some problems, both solutions are meaningful, but in others, such as the above, only one solution is reasonable. The 10s answer seems reasonable for a typical freeway on-ramp. With the basics of kinematics established, we can go on to many other interesting examples and applications. In the process of developing kinematics, we have also glimpsed a general approach to problem solving that produces both correct answers and insights into physical relationships. Problem Solving Basics discusses problem-solving basics and outlines an approach that will help you succeed in this invaluable task. Making connections, take-home experiment, breaking news. We have been using SI units of meters per second squared to describe some examples of acceleration or deceleration of cars, runners, and trains. To achieve a better feel for these numbers, one can measure the braking deceleration of a car doing a slow and safe stop. Recall that, for average acceleration, letter 1d440 equals delta letter 1d463 slash delta letter 1d461. While traveling in a car, slowly apply the brakes as you come up to a stop sign. Have a passenger note the initial speed in miles per hour and the time taken in seconds to stop. From this, calculate the deceleration in miles per hour per second. Convert this to meters per second squared and compare with other decelerations mentioned in this chapter. Calculate the distance traveled in braking. Check your understanding. A rocket accelerates at a rate of 20 ms2. During launch, How long does it take the rocket to reach a velocity of 400 ms? Solution. To answer this, choose an equation that allows you to solve for time t. Given only a v0, and v letter 1d463 equals letter 1d4630 plus letter 1d44 letter 1d461. 2.7. Rearrange to solve for t. Letter 1d461 equals letter 1d463 minus letter 1d463, 0 letter 1d44 equals 400 m/s minus 0, ms 20 m/s2 equals 20s. 2.71. By the end of this section, you will be able to apply problem-solving steps and strategies to solve problems of one-dimensional kinematics. Apply strategies to determine whether or not the result of a problem is reasonable, and if not, determine the cause. Close-up photo of a hand writing in a notebook. On top of the notebook is a graphing calculator. Figure 2.36, problem-solving skills are essential to your success in physics. Credit, SKUI 3 Estiveo Flickr. Problem-solving skills are obviously essential to success in a quantitative course in physics. More importantly, the ability to apply broad physical principles, usually represented by equations, to specific situations is a very powerful form of knowledge. It is much more powerful than memorizing a list of facts. Analytical skills and problem-solving abilities can be applied to new situations, whereas a list of facts cannot be made long enough to contain every possible circumstance. Such analytical skills are useful both for solving problems in this text and for applying physics in everyday and professional life. Problem-solving steps. While there is no simple step-by-step method that works for every problem, the following general procedures facilitate problem solving and make it more meaningful. A certain amount of creativity and insight is required as well. Step 1. Examine the situation to determine which physical principles are involved. It often helps to draw a simple sketch at the outset. You will also need to decide which direction is positive and note that on your sketch. Once you have identified the physical principles, it is much easier to find and apply the equations representing those principles. Although finding the correct equation is essential, keep in mind that equations represent physical principles, laws of nature, and relationships among physical quantities. Without a conceptual understanding of a problem, a numerical solution is meaningless. Step 2. Make a list of what is given or can be inferred from the problem as stated. Identify the knowns. Many problems are stated very succinctly and require some inspection to determine what is known. A sketch can also be very useful at this point. Formally identifying the knowns is of particular importance in applying physics to real-world situations. Remember, stopped means velocity is 0, and we often can take initial time and position as 0. Step 3. Identify exactly what needs to be determined in the problem. Identify the unknowns. In complex problems, especially, it is not always obvious what needs to be found or in what sequence. Making a list can help. Step 4. Find an equation or set of equations that can help you solve the problem. Your list of knowns and unknowns can help here. It is easiest if you can find equations that contain only one unknown. That is, all of the other variables are known, so you can easily solve for the unknown. If the equation contains more than one unknown, then an additional equation is needed to solve the problem. In some problems, several unknowns must be determined to get at the one needed most. In such problems, it is especially important to keep physical principles in mind to avoid going astray in a sea of equations. You may have to use 2 or more different equations to get the final answer. Step 5. Substitute the knowns along with their units into the appropriate equation and obtain numerical solutions complete with units. This step produces the numerical answer. It also provides a check on units that can help you find errors. If the units of the answer are incorrect, then an error has been made. However, be warned that correct units do not guarantee that the numerical part of the answer is also correct. Step 6. Check the answer to see if it is reasonable. Does it make sense? This final step is extremely important. The goal of physics is to accurately describe nature. To see if the answer is reasonable, check both its magnitude and its sign, in addition to its units. Your judgment will improve as you solve more and more physics problems, and it will become possible for you to make finer and finer judgments regarding whether nature is adequately described by the answer to a problem. This step brings the problem back to its conceptual meaning. If you can judge whether the answer is reasonable, you have a deeper understanding of physics than just being able to mechanically solve a problem. When solving problems, we often perform these steps in different order, and we also tend to do several steps simultaneously. There is no rigid procedure that will work every time. Creativity and insight grow with experience, and the basics of problem solving become almost automatic. One way to get practice is to work out the text examples for yourself as you read. Another is to work as many end-of-section problems as possible, starting with the easiest to build confidence and progressing to the more difficult. Once you become involved in physics, you will see it all around you, and you can begin to apply it to situations you encounter outside the classroom, just as is done in many of the applications in this text. Unreasonable results. Physics must describe nature accurately. Some problems have results that are unreasonable because one premise is unreasonable or because certain premises are inconsistent with one another. The physical principle applied correctly then produces an unreasonable result. For example, if a person starting a foot race accelerates at 0.4 ms2. For 100s, his final speed will be 40 ms, about 150 km/h. Clearly unreasonable because the time of 100s is an unreasonable premise. The physics is correct in a sense, but there is more to describing nature than just manipulating equations correctly. Checking the result of a problem to see if it is reasonable does more than help uncover errors in problem solving. It also builds intuition in judging whether nature is being accurately described. Use the following strategies to determine whether an answer is reasonable, and, if it is not, to determine what is the cause. Step 1. Solve the problem using strategies as outlined and in the format followed in the worked examples in the text. In the example given in the preceding paragraph, you would identify the givens as the acceleration and time and use the equation below to find the unknown final velocity. That is, letter 1d463 equals letter 1d4630 plus letter 1d44 letter 1d461 equals 0 plus 0. 40 m/s2. 100s equals 40 m/s. 2.72. Step 2. Check to see if the answer is reasonable. Is it too large or too small, or does it have the wrong sign, improper units? In this case, you may need to convert meters per second into a more familiar unit, such as miles per hour. 40 ms, 3, 28 ftm, 1 me 5280 ft, 60 smin, 60 min 1 h equals 89 mph. 2.73. This velocity is about 4 times greater than a person can run, so it is too large. Step 3. If the answer is unreasonable, look for what specifically could cause the identified difficulty. In the example of the runner, there are only 2 assumptions that are suspect. The acceleration could be too great or the time too long. First, look at the acceleration and think about what the number means. If someone accelerates at 0.4 ms2, their velocity is increasing by 0.4 ms each second. Does this seem reasonable? If so, the time must be too long. It is not possible for someone to accelerate at a constant rate of 0.4 ms2. For 100s, almost 2 minutes. Learning objectives. By the end of this section, you will be able to describe the effects of gravity on objects in motion. Describe the motion of objects that are in free fall. Calculate the position and velocity of objects in free fall. Falling objects form an interesting class of motion problems. For example, we can estimate the depth of a vertical mine shaft by dropping a rock into it and listening for the rock to hit the bottom. By applying the kinematics developed so far to falling objects, we can examine some interesting situations and learn much about gravity in the process. Gravity. The most remarkable and unexpected fact about falling objects is that, if air resistance and friction are negligible, then in a given location, all objects fall toward the center of Earth with the same constant acceleration, independent of their mass. This experimentally determined fact is unexpected because we are so accustomed to the effects of air resistance and friction that we expect light objects to fall slower than heavy ones. Positions of a feather and hammer over time as they fall on the moon. The feather and hammer are at the exact same position at each moment in time. Figure 2.37, a hammer and a feather will fall with the same constant acceleration if air resistance is considered negligible. This is a general characteristic of gravity not unique to Earth, as astronaut David R. Scott demonstrated on the Moon in 1971, where the acceleration due to gravity is only 1/67 ms2. In the real world, air resistance can cause a lighter object to fall slower than a heavier object of the same size. A tennis ball will reach the ground after a hard baseball dropped at the same time. It might be difficult to observe the difference if the height is not large. Air resistance opposes the motion of an object through the air, while friction between objects, such as between clothes and a laundry chute or between a stone and a pool into which it is dropped, also opposes motion between them. For the ideal situations of these first few chapters, an object falling without air resistance or friction is defined to be in freefall. The force of gravity causes objects to fall toward the center of Earth. The acceleration of free-falling objects is therefore called the acceleration due to gravity. The acceleration due to gravity is constant, which means we can apply the kinematics equations to any falling object where air resistance and friction are negligible. This opens a broad class of interesting situations to us. The acceleration due to gravity is so important that its magnitude is given its own symbol, letter 1d454. It is constant at any given location on Earth and has the average value. Letter 1d454 equals 980 ms2. 2.74. Although letter 1d454 varies from 978 ms2 to 9.83 ms2. Depending on latitude, altitude, underlying geological formations, and local topography, the average value of 980 ms2 will be used in this text unless otherwise specified. The direction of the acceleration due to gravity is downward, towards the center of Earth. In fact, its direction defines what we call vertical. Note that whether the acceleration, letter 1d44e, in the kinematic equations, has the value plus letter 1d454, or minus letter 1d454, depends on how we define our coordinate system. If we define the upward direction as positive, then letter 1d44e equals minus letter 1d454 equals minus 980 ms2. And if we define the downward direction as positive, then letter 1d44e equals letter 1d454 equals 980 ms2. One-dimensional motion involving gravity. The best way to see the basic features of motion involving gravity is to start with the simplest situations and then progress toward more complex ones. So we start by considering straight up and down motion with no air resistance or friction. These assumptions mean that the velocity, if there is any, is vertical. If the object is dropped, we know the initial velocity is 0. Once the object has left contact with whatever held or threw it, the object is in free fall. Under these circumstances, the motion is one-dimensional and has constant acceleration of magnitude letter 1d454. We will also represent vertical displacement with the symbol letter 1d466 and use letter 1d465. For horizontal displacement, kinematic equations for objects in free fall where acceleration equals g. Letter 1d463 equals letter 1d463, 0 minus letter 1d454 letter 1d461. 2.75. Letter 1d466 equals letter 1d4660 plus letter 1d4630, letter 1d461, minus 12 letter 1d454 letter 1d461, 2. 2.76. Letter 1d463, 2 equals letter 1d463, 20 minus 2, letter 1d454, letter 1d466, minus letter 1d4660. 2.77. Example 2.14. Calculating position and velocity of a falling object, a rock thrown upward. A person standing on the edge of a high cliff throws a rock straight up with an initial velocity of 13 ms, the rock misses the edge of the cliff as it falls back to Earth. Calculate the position and velocity of the rock 1s, 2s, and 3s after it is thrown, neglecting the effects of air resistance. Strategy: draw a sketch. Velocity vector arrow pointing up in the positive y direction, labeled v sub 0, equals 13.0 meters per second. Acceleration vector arrow pointing down in the negative y direction, labeled at equals negative 9.8 meters per second squared. Figure 2.38. We are asked to determine the position, letter 1D466. At various times, it is reasonable to take the initial position, letter 1D4660, to be 0. This problem involves one-dimensional motion in the vertical direction. We use plus and minus signs to indicate direction, with up being positive and down negative. Since up is positive and the rock is thrown upward, the initial velocity must be positive too. The acceleration due to gravity is downward, so letter 1D44E is negative. It is crucial that the initial velocity and the acceleration due to gravity have opposite signs. Opposite signs indicate that the acceleration due to gravity opposes the initial motion and will slow and eventually reverse it. Since we are asked for values of position and velocity at 3 times, we will refer to these as letter 1D4661, and letter 1D4631, letter 1D4662, and letter 1D4632, and letter 1D4663, and letter 1D4633. Solution for position. Y1. 1. Identify the knowns. We know that letter 1D4660 equals 0. Letter 1D4630 equals 13, 0 ms. Letter 1D44 equals minus letter 1D454 equals minus 9, 80 ms2. And letter 1D461 equals 1, 0, 0 s. 2. Identify the best equation to use. We will use letter 1D466 equals letter 1D4660 plus letter 1D4630, letter 1D461, plus 12 letter 1D44, letter 1D461, 2. Because it includes only one unknown, letter 1D466, or letter 1D4661. Here, which is the value we want to find? 3. Plug in the known values and solve for letter 1D4661. Letter 1D4661 equals 0 plus 13, 0 m/s. 1, 0, 0 s plus 12 minus 9, 80 m/s2, 1, 0, 0 s2 equals 8, 10 m. 2.78. Discussion. The rock is 8.1 m above its starting point at letter 1D461 equals 1, 0, 0. S, since letter 1D4661, letter 1D4660. It could be moving up or down. The only way to tell is to calculate letter 1D4631 and find out if it is positive or negative. Solution for velocity. V1. 1. Identify the knowns. We know that letter 1D4660 equals 0. Letter 1D4630 equals 13, 0 ms. Letter 1D44 equals minus letter 1D454 equals minus 9, 80 ms2. And letter 1D461 equals 1, 0, 0 s. We also know from the solution above that letter 1D4661 equals 8, 10 m. 2. Identify the best equation to use. The most straightforward is letter 1D463 equals letter 1D463, 0 minus letter 1D454, letter 1D461. From letter 1D463 equals letter 1D4630 plus letter 1D44, letter 1D461. Where letter 1D44 equals gravitational acceleration equals minus letter 1D454. 3. Plug in the knowns and solve. Letter 1D4631 equals letter 1D463, 0 minus letter 1D454, letter 1D461 equals 13, 0 m/s minus 9, 80 m/s2, 1, 0, 0 s equals 3, 20 ms. 2.79. Discussion. The positive value for letter 1D463, 1. means that the rock is still heading upward at letter 1d461 equals 1, 0, 0. However, it has slowed from its original 13 ms, as expected. Solution for remaining times. The procedures for calculating the position and velocity at letter 1d461 equals 2, 0, 0, and 3, 0, 0s are the same as those above. The results are summarized in Table 2.1 and illustrated in Figure 2.39. Time t position, y velocity v acceleration. 1s, 8.1 m, 3.2 ms, minus 9, 80 ms2. 2s, 6.4 m, minus 6, 60 ms, minus 9, 80 ms2. 3s, minus 5, 10 m, minus 16, 4 ms, minus 9, 80 ms2. Table 2.1 results. Graphing the data helps us understand it more clearly. 3 panels showing 3 graphs. The top panel shows a graph of vertical position in meters versus time in seconds. The line begins at the origin and has a positive slope that decreases over time until it hits a turning point between seconds 1 and 2. After that, it has a negative slope that increases over time. The middle panel shows a graph of velocity in meters per second versus time in seconds. The line is straight, with a negative slope, beginning at time 0 velocity of 13 meters per second and ending at time 3 seconds with a velocity just over negative 16 meters per second. The bottom panel shows a graph of acceleration in meters per second squared versus time in seconds. The line is straight and flat at a y value of negative 9.80 meters per second squared from time 0 to time 3 seconds. Figure 2.39 vertical position, vertical velocity, and vertical acceleration versus time for a rock thrown vertically up at the edge of a cliff. Notice that velocity changes linearly with time and that acceleration is constant. Misconception alert. Notice that the position versus time graph shows vertical position only. It is easy to get the impression that the graph shows some horizontal motion. The shape of the graph looks like the path of a projectile. But this is not the case. The horizontal axis is time, not space. The actual path of the rock in space is straight up and straight down. Discussion. The interpretation of these results is important. At 1s, the rock is above its starting point and heading upward, since letter 1d4661 and letter 1d4631 are both positive. At 2s, the rock is still above its starting point, but the negative velocity means it is moving downward. At 3s, both letter 1d4663 and letter 1d4633 are negative, meaning the rock is below its starting point and continuing to move downward. Notice that when the rock is at its highest point, at 1.33s, its velocity is 0, but its acceleration is still minus 9, 80 ms2. Its acceleration is minus 9, 80 ms2. For the whole trip, while it is moving up and while it is moving down. Note that the values for letter 1d466 are the positions or displacements of the rock, not the total distances traveled. Finally, note that freefall applies to upward motion as well as downward. Both have the same acceleration, the acceleration due to gravity, which remains constant the entire time. Astronauts training in the famous Vomit Comet, for example, experience freefall while arcing up as well as down, as we will discuss in more detail later. Making connections, take-home experiment, reaction time. A simple experiment can be done to determine your reaction time. Have a friend hold a ruler between your thumb and index finger, separated by about 1 cm. Note the mark on the ruler that is right between your fingers. Have your friend drop the ruler unexpectedly and try to catch it between your 2 fingers. Note the new reading on the ruler. Assuming acceleration is that due to gravity, calculate your reaction time. How far would you travel in a car, moving at 30 ms, if the time it took your foot to go from the gas pedal to the brake was twice this reaction time? Example 2.15. Calculating velocity of a falling object, a rock thrown down. What happens if the person on the cliff throws the rock straight down instead of straight up? To explore this question, calculate the velocity of the rock when it is 5.1 m below the starting point and has been thrown downward with an initial speed of 13 ms. Strategy. Draw a sketch. Velocity vector arrow pointing down in the negative y direction and labeled v sub 0 equals negative 13.0 meters per second. Acceleration vector arrow also pointing down in the negative y direction, labeled a equals negative 9.80 meters per second squared. Figure 2.4. Since up is positive, the final position of the rock will be negative, because it finishes below the starting point at letter 1d4660 equals 0. Similarly, the initial velocity is downward and therefore negative, as is the acceleration due to gravity. We expect the final velocity to be negative since the rock will continue to move downward. Solution. 1. Identify the knowns. Letter 1d4660 equals 0. Letter 1d4661 equals minus 5, 10 m. Letter 1d4630 equals minus 13, 0 ms. Letter 1d440 equals minus letter 1d454 equals minus 9, 80 ms2. 2. Choose the kinematic equation that makes it easiest to solve the problem. The equation letter 1d463 2 equals letter 1d463 20 plus 2 letter 1d440, letter 1d466 minus letter 1d466 0. Works well because the only unknown in it is letter 1d463. We will plug letter 1d4661 in for letter 1d466. 3. Enter the known values. Letter 1d4632 equals minus 13, 0 m slash s2 plus 2 minus 9, 80 m slash s2, minus 5, 10 m minus 0 m equals 268, 96 m2 s2. 2.8. Where we have retained extra significant figures, because this is an intermediate result. Taking the square root and noting that a square root can be positive or negative gives letter 1d463 equals plus 16, 4 ms. 2.81. The negative root is chosen to indicate that the rock is still heading down. Thus, letter 1d463 equals minus 16, 4 ms. 2.82. Discussion. Note that this is exactly the same velocity the rock had at this position when it was thrown straight upward with the same initial speed. See example 2.14 and figure 2.41. A. This is not a coincidental result. Because we only consider the acceleration due to gravity in this problem, the speed of a falling object depends only on its initial speed and its vertical position relative to the starting point. For example, if the velocity of the rock is calculated at a height of 8.1 m above the starting point, using the method from example 2.14, when the initial velocity is 13 ms straight up, a result of plus or minus 3, 20 ms, is obtained. Here both signs are meaningful. The positive value occurs when the rock is at 8.1 m and heading up, and the negative value occurs when the rock is at 8.1 m and heading back down. It has the same speed but the opposite direction. Two figures are shown. At left, a man standing on the edge of a cliff throws a rock straight up with an initial speed of 13 meters per second. At right, the man throws the rock straight down with a speed of 13 meters per second. In both figures, a line indicates the rock's trajectory. When the rock is thrown straight up, it has a speed of minus 16.4 meters per second at minus 5.10 meters below the point where the man released the rock. When the rock is thrown straight down, the velocity is the same at this position. Figure 2.41a. A person throws a rock straight up, as explored in example 2.14. The arrows are velocity vectors at 0, 1, 2, and 3s. B. A person throws a rock straight down from a cliff with the same initial speed as before, as in example 2.15. Note that at the same distance below the point of release, the rock has the same velocity in both cases. Another way to look at it is this. In example 2.14, the rock is thrown up with an initial velocity of 13, 0 ms. It rises and then falls back down, when its position is. On its way back down, its velocity is minus 13, 0 ms. That is, it has the same speed on its way down as on its way up. We would then expect its velocity at a position of letter 1d466 equals minus 5, 10 m. To be the same whether we have thrown it upwards at plus 13, 0 ms. or thrown it downwards at -13, 0 ms. The velocity of the rock on its way down from letter 1d466 equals 0 is the same whether we have thrown it up or down to start with, as long as the speed with which it was initially thrown is the same. Example 2.16. Find g from data on a falling object. The acceleration due to gravity on Earth differs slightly from place to place, depending on topography, e.g., whether you are on a hill or in a valley, and subsurface geology, whether there is dense rock like iron ore as opposed to light rock like salt beneath you. The precise acceleration due to gravity can be calculated from data taken in an introductory physics laboratory course. An object, usually a metal ball for which air resistance is negligible, is dropped and the time it takes to fall a known distance is measured. See, for example, Figure 2.42. Very precise results can be produced with this method if sufficient care is taken in measuring the distance fallen and the elapsed time. Figure has 4 panels. The first panel on the top is an illustration of a ball falling toward the ground at intervals of 1/10 of a second. The space between the vertical position of the ball at one time step and the next increases with each time step. At time equals 0, position and velocity are also 0. At time equals 0.1 seconds, y position equals -0.49 meters and velocity is -0.98 meters per second. At 0.5 seconds, y position is -1.225 meters and velocity is -4.90 meters per second. The second panel in the middle is a line graph of position in meters versus time in seconds. Line begins at the origin and slopes down with increasingly negative slope. The third panel, bottom left, is a line graph of velocity in meters per second versus time in seconds. Line is straight, beginning at the origin and with a constant negative slope. The fourth panel, bottom right, is a line graph of acceleration in meters per second squared versus time in seconds. Line is flat, at a constant y value of -9.80 meters per second squared. Figure 2.42 positions and velocities of a metal ball released from rest when air resistance is negligible. Velocity is seen to increase linearly with time, while displacement increases with time squared. Acceleration is a constant and is equal to gravitational acceleration. Suppose the ball falls 1 m in 0.45173 s, assuming the ball is not affected by air resistance. What is the precise acceleration due to gravity at this location? Strategy. Draw a sketch. The figure shows a green dot labeled v sub 0 equals 0 meters per second, a purple downward pointing arrow labeled a equals question mark, and an XY coordinate system with the y-axis pointing vertically up and the x-axis pointing horizontally to the right. Figure 2.43. We need to solve for acceleration, letter 1d440. Note that in this case, displacement is downward and therefore negative, as is acceleration. Solution. 1. Identify the knowns. Letter 1d4660 equals 0. Letter 1d466 equals 1, 0, 0, 0, 0 m. Letter 1d461 equals 0, 45,173. Letter 1d4630 equals 0. 2. Choose the equation that allows you to solve for letter 1d440. Using the known values. Letter 1d466 equals letter 1d4660 plus letter 1d4630, letter 1d461, plus 12 letter 1d440, letter 1d461, 2. 2.83. 3. Substitute 0 for letter 1d4630 and rearrange the equation to solve for letter 1d440. Substituting 0 for letter 1d4630 yields letter 1d466 equals letter 1d4660 plus 12 letter 1d440, letter 1d461, 2. 2.84. Solving for letter 1d440 gives letter 1d440 equals 2, letter 1d466 minus letter 1d466, 0, letter 1d461, 2. 2.85. 4. Substitute known values yields. Letter 1d440 equals 2 minus 1, 0, 0, 0, 0 m, 0, 0, 45,173 S2 equals minus 9, 8,010 M S2. 2.86. So, because letter 1D44E equals minus letter 1D454. With the directions we have chosen, letter 1D454 equals 9, 8,010 M S2. 2.87. Discussion. The negative value for letter 1D44E indicates that the gravitational acceleration is downward, as expected. We expect the value to be somewhere around the average value of 9, 80 ms2. So 9, 8010 ms2 makes sense. Since the data going into the calculation are relatively precise, this value for letter 1D454 is more precise than the average value of 9, 80 ms2. It represents the local value for the acceleration due to gravity. Check your understanding. A chunk of ice breaks off a glacier and falls 30 meters before it hits the water. Assuming it falls freely, there is no air resistance. How long does it take to hit the water? Solution. We know that initial position, letter 1D4660, equals 0. Final position, letter 1D466 equals minus 30, 0 m. And letter 1D44E equals minus letter 1D454 equals minus 9, 80 ms2. We can then use the equation letter 1D466 equals letter 1D4660 plus letter 1D463, letter 1D461, plus 12 letter 1D44 letter 1D461, 2. To solve for letter 1D461, inserting letter 1D44E equals minus letter 1D454. We obtain plus 0 minus 12 letter 1D454 letter 1D461, 22 letter 1D466 minus letter 1D454 plus, or minus 2 letter 1D466 minus letter 1D454, square equals plus 2, minus 30. 0 m minus 9, 80 m slash s2 square equals plus 6. 12's 2 square equals 2, 47 s approximately 2, 5 s. 2.88. Where we take the positive value as the physically relevant answer. Thus, it takes about 2.5 seconds for the piece of ice to hit the water. pH at explorations. Equation grapher. Learn about graphing polynomials. The shape of the curve changes as the constants are adjusted. View the curves for the individual terms, e.g., to see how they add to generate the polynomial curve. Learning objectives. By the end of this section, you will be able to describe a straight line graph in terms of its slope and y-intercept. Determine average velocity or instantaneous velocity from a graph of position versus time. Determine average or instantaneous acceleration from a graph of velocity versus time. Derive a graph of velocity versus time from a graph of position versus time. Derive a graph of acceleration versus time from a graph of velocity versus time. A graph, like a picture, is worth 1,000 words. Graphs not only contain numerical information, they also reveal relationships between physical quantities. This section uses graphs of position, velocity, and acceleration versus time to illustrate one-dimensional kinematics. Slopes and general relationships. First, note that graphs in this text have perpendicular axes, one horizontal and the other vertical. When two physical quantities are plotted against one another in such a graph, the horizontal axis is usually considered to be an independent variable and the vertical axis a dependent variable. If we call the horizontal axis the x-axis and the vertical axis the y-axis, as in figure 2.44, a straight line graph has the general form. Letter 1D466 equals letter 1D45A letter 1D465 plus letter 1D44F. 2.89. Here m is the slope, defined to be the rise divided by the run, as seen in the figure of the straight line. The letter b is used for the y-intercept, which is the point at which the line crosses the vertical axis. Graph of a straight line sloping up at about 40 degrees. Figure 2.44, a straight line graph. The equation for a straight line is letter 1D466 equals letter 1D45A letter 1D465 plus letter 1D44F. Graph of position versus time, a equals 0, so v is constant. Time is usually an independent variable that other quantities, such as position, depend upon. A graph of position versus time would, thus, have x on the vertical axis and t on the horizontal axis. Figure 2.45 is just such a straight-line graph. It shows a graph of position versus time for a jet-powered car on a very flat, dry lake bed in Nevada. Line graph of jet car displacement in meters versus time in seconds. The line is straight with a positive slope. The y-intercept is 400 meters. The total change in time is 8.0 seconds. The initial position is 400 meters. The final position is 2,000 meters. Figure 2.45 graph of position versus time for a jet-powered car on the Bonneville Salt Flats. Using the relationship between dependent and independent variables, we see that the slope in the graph above is average velocity, letter 1 d463. And the intercept is position at time 0, that is, x0. Substituting these symbols into letter 1 d466 equals letter 1 d45a letter 1 d465 plus letter 1 d44f gives letter 1 d465 equals letter 1 d463 letter 1 d461 plus letter 1 d4650. 2.9 or letter 1 d465 equals letter 1 d4650 plus letter 1 d463 letter 1 d461. 2.91. Thus, a graph of position versus time gives a general relationship among displacement, change in position, velocity, and time, as well as giving detailed numerical information about a specific situation. The slope of x v is t. The slope of the graph of position x versus time t is velocity v. Slope equals delta letter 1 d465, delta letter 1 d461 equals letter 1 d463. 2.92. Notice that this equation is the same as that derived algebraically from other motion equations, in motion equations for constant acceleration in one dimension. From the figure, we can see that the car has a position of 525 m at 0.5 s and 2000 m at 6.4 s. Its position at other times can be read from the graph. Furthermore, information about its velocity and acceleration can also be obtained from the graph. Example 2.17. Determining average velocity from a graph of position versus time. Jet car. Find the average velocity of the car, whose position is graphed in figure 2.45. Strategy. The slope of a graph of x of v is t is average velocity, since slope equals rise over run. In this case, rise equals change in position and run equals change in time, so that slope equals delta letter 1 d465, delta letter 1 d461 equals letter 1 d463. 2.93. Since the slope is constant here, any 2 points on the graph can be used to find the slope. Generally speaking, it is most accurate to use 2 widely separated points on the straight line. This is because any error in reading data from the graph is proportionally smaller if the interval is larger. Solution. 1. Choose 2 points on the line. In this case, we choose the points labeled on the graph: 6.4 s, 2000 m, and 0.5 s, 525 m. Note, however, that you could choose any 2 points. 2. Substitute the x and t values of the chosen points into the equation. Remember, in calculating change, delta, we always use final value minus initial value. Letter 1 d463 equals delta letter 1 d465, delta letter 1 d461 equals 2000 m minus 525 m64 s minus 0, 50 s. 2.94. Yielding. Letter 1 d463 equals 250 ms. 2.95. Discussion. This is an impressively large land speed, 900 km/h, or about 560 mph, much greater than the typical highway speed limit of 60 mph, 27 ms or 96 km/h, but considerably shy of the record of 343 ms, 1234 km/h or 766 mph, set in 1997. Graphs of motion when A is constant but letter 1d440, not equal to 0. The graphs in figure 2.46 below represent the motion of the jet-powered car as it accelerates toward its top speed, but only during the time when its acceleration is constant. Time starts at 0 for this motion, as if measured with a stopwatch, and the position and velocity are initially 200 m and 15 ms, respectively. 3-line graphs. First is a line graph of displacement over time. Line has a positive slope that increases with time. Second line graph is of velocity over time. Line is straight with a positive slope. Third line graph is of acceleration over time. Line is straight and horizontal, indicating constant acceleration. Figure 2.46 graphs of motion of a jet-powered car during the time span when its acceleration is constant. A, the slope of an x. T. Graph is velocity. This is shown at 2 points, and the instantaneous velocities obtained are plotted in the next graph. Instantaneous velocity at any point is the slope of the tangent at that point. B, the slope of the v. T. Graph is constant for this part of the motion, indicating constant acceleration. C, acceleration has the constant value of 5 ms2. Over the time interval plotted. A photo shows a U.S. Air Force jet speeding down a track with a lot of smoke around it. Figure 2.47, a U.S. Air Force jet car speeds down a track. Credit, Matt Trossel Flickr. The graph of position versus time in Figure 2.46, A is a curve rather than a straight line. The slope of the curve becomes steeper as time progresses, showing that the velocity is increasing over time. The slope at any point on a position versus time graph is the instantaneous velocity at that point. It is found by drawing a straight line tangent to the curve at the point of interest and taking the slope of this straight line. Tangent lines are shown for 2 points in Figure 2.46a. If this is done at every point on the curve and the values are plotted against time, then the graph of velocity versus time shown in Figure 2.46b is obtained. Furthermore, the slope of the graph of velocity versus time is acceleration, which is shown in Figure 2.46c. Example 2.18. Determining instantaneous velocity from the slope at a point. Jet car. Calculate the velocity of the jet car at a time of 25 s by finding the slope of the x. T. Graph in the graph below. A graph of displacement versus time for a jet car. The x-axis for time runs from 0 to 35 seconds. The y-axis for displacement runs from 0 to 3,000 meters. The curve depicting displacement is concave up. The slope of the curve increases over time. Slope equals velocity v. There are 2 points on the curve, labeled P and QP is located at time equals 10 seconds. Q is located, and time equals 25 seconds. A line tangent to P at 10 seconds is drawn and has a slope delta x sub P over delta T sub P. A line tangent to Q at 25 seconds is drawn and has a slope equal to delta x sub Q over delta T sub Q. Select coordinates are given in a table and consist of the following. Time 0 seconds displacement 200 meters. Time 5 seconds displacement 338 meters. Time 10 seconds displacement 600 meters. Time 15 seconds displacement 988 meters. Time 20 seconds displacement 1,500 meters. Time 25 seconds displacement 2,138 meters. Time 30 seconds displacement 2,900 meters. Figure 2.48, the slope of an x. T. Graph is velocity. This is shown at 2 points. Instantaneous velocity at any point is the slope of the tangent at that point. Strategy. The slope of a curve at a point is equal to the slope of a straight line tangent to the curve at that point. This principle is illustrated in Figure 2.48, where Q is the point at letter 1d461 equals 25s. Solution. 1. Find the tangent line to the curve at letter 1d461 equals 25s. 2. Determine the endpoints of the tangent. These correspond to a position of 1300 m at time 19 s and a position of 3120 m at time 32 s. 3. Plug these endpoints into the equation to solve for the slope, v. Slope equals letter 1d463, q equals delta letter 1d465, q delta letter 1d461, q equals 3120 m minus 1300 m. 32 s minus 19s. 2.96. Thus, letter 1d463, q equals 1820 m13, s equals 140 ms. 2.97. Discussion. This is the value given in this figure's table for V. At letter 1d461 equals 25s. The value of 140 ms for VQ is plotted in figure 2.48, the entire graph of V. V's t can be obtained in this fashion. Carrying this one step further, we note that the slope of a velocity versus time graph is acceleration. Slope is rise divided by run on a V. V's t graph, rise equals change in velocity delta, letter 1d463. And run equals change in time, delta letter 1d461. The slope of V's t. The slope of a graph of velocity V versus time t is acceleration a. Slope equals delta letter 1d463, delta letter 1d461 equals letter 1d440. 2.98. Since the velocity versus time graph in figure 2.46b is a straight line, its slope is the same everywhere, implying that acceleration is constant. Acceleration versus time is graphed in figure 2.46c. Additional general information can be obtained from figure 2.48, and the expression for a straight line, letter 1d466 equals letter 1d45a letter 1d465 plus letter 1d44f. In this case, the vertical axis y is v, the intercept b is v0, the slope m is a, and the horizontal axis x is t. Substituting these symbols yields letter 1d463 equals letter 1d4630 plus letter 1d44 letter 1d461. 2.99. A general relationship for velocity, acceleration, and time has again been obtained from a graph. Notice that this equation was also derived algebraically from other motion equations in motion equations for constant acceleration in one dimension. It is not accidental that the same equations are obtained by graphical analysis as by algebraic techniques. In fact, an important way to discover physical relationships is to measure various physical quantities, and then make graphs of one quantity against another to see if they are correlated in any way. Correlations imply physical relationships and might be shown by smooth graphs such as those above. From such graphs, mathematical relationships can sometimes be postulated. Further experiments are then performed to determine the validity of the hypothesized relationships. Graphs of motion where acceleration is not constant. Now consider the motion of the jet car as it goes from 165 ms to its top velocity of 250 ms, graphed in figure 2.49. Time again starts at 0, and the initial velocity is 165 ms. This was the final velocity of the car in the motion graphed in figure 2.46. Acceleration gradually decreases from 5 ms2 to 0 when the car hits 250 ms. The velocity increases until 55 s and then becomes constant, since acceleration decreases to 0 at 55 s and remains 0 afterward. Two line graphs of jet car velocity and acceleration, respectively. First line graph is of velocity over time. Line graph has a positive slope that decreases over time and flattens out at the end. Second line graph is of acceleration over time. Line has a negative slope that increases over time until it flattens out at the end. The line is not smooth, but has several kinks. Figure 2.49 graphs of motion of a jet-powered car as it reaches its top velocity. This motion begins where the motion in figure 2.46 ends. A. The velocity gradually approaches its top value. The slope of this graph is acceleration. It is plotted in the final graph. B. Acceleration gradually declines to 0 when velocity becomes constant. Notice in each of the three graphs that the acceleration drops down to 0 and the velocity levels out. This results in a position time graph that is almost linear. A close-up of the position time graph would show a slight curvature, as indicated in the velocity graph. Example 2.19. Calculating acceleration from a graph of velocity versus time. Calculate the acceleration of the jet car at a time of 25s by finding the slope of the v. V's t. Graph in Figure 2, 49a. Strategy. The slope of the curve at letter 1D461 equals 25s is equal to the slope of the line tangent at that point, as illustrated in Figure 2, 49a. Solution. Determine endpoints of the tangent line from the figure, and then plug them into the equation to solve for slope a. Slope equals delta letter 1D463, delta letter 1D461 equals 260m/s minus 210m/s, 51s minus 1, 0s. 2.1. Letter 1D440 equals 50ms, 50s equals 1, 0 ms2. 2.101. Discussion. Note that this value for a is consistent with the value plotted in Figure 2, 49b, at letter 1D461 equals 25s. A graph of position versus time can be used to generate a graph of velocity versus time, and a graph of velocity versus time can be used to generate a graph of acceleration versus time. We do this by finding the slope of the graphs at every point. If the graph is linear, i.e., a line with a constant slope, it is easy to find the slope at any point, and you have the slope for every point. Graphical analysis of motion can be used to describe both specific and general characteristics of kinematics. Graphs can also be used for other topics in physics. An important aspect of exploring physical relationships is to graph them and look for underlying relationships. Check your understanding. A graph of velocity versus time of a ship coming into a harbor is shown below. A. Describe the motion of the ship based on the graph. B. What would a graph of the ship's acceleration look like? Line graph of velocity versus time. The line has 3 legs. The first leg is flat. The second leg has a negative slope. The third leg also has a negative slope, but the slope is not as negative as the second leg. Figure 2.5. Solution. A. The ship moves at constant velocity and then begins to decelerate at a constant rate. At some point, its deceleration rate decreases. It maintains this lower deceleration rate until it stops moving. B. A graph of acceleration versus time would show 0 acceleration in the first leg, large and constant negative acceleration in the second leg, and constant negative acceleration. A line graph of acceleration versus time. There are 3 legs of the graph. All 3 legs are flat and straight. The first leg shows constant acceleration of 0. The second leg shows a constant negative acceleration. The third leg shows a constant negative acceleration that is not as negative as the second leg. Figure 2.51.